All right. Hi, everyone. Welcome to the RI seminar. It's my great pleasure today to introduce our RI seminar speaker, Raquel Urtasun. Raquel is the chief scientist at Uber ATG and head of Uber ATG in Toronto. She's also a full professor in the Department of Computer Science at the University of Toronto. She's a Canada Research Chair in Machine Learning and Computer Vision, and she's a co-founder of the Vector Institute for AI. She's also a recipient of numerous awards, which there are too many to name, but I'll just name a few. She received the NSERC, which is the Natural Sciences and Engineering Research Council of Canada, EWR Stacy Award, which is an award given to the best scientists by, currently given by Trudeau. She also received the Ministry of Education and Innovation Early Researcher Award, and numerous awards from NVIDIA and other sources. On a personal level, I have looked up to Raquel since my PhD. She has always been one of the world leaders in computer vision, starting from her early work on human pose tracking. She later went on to do pioneering research on 3D reasoning and a lot of fundamental machine learning work. And now she's doing incredible work on vision for autonomous driving. Also, before we start, I want to mention that after this, there will be a reception in the Gather Town. I posted the link in the chat where everyone can get together to hang out and chat or meet with Raquel. So let's all welcome Raquel, and I look forward to hearing her talk.
Thanks, Dave, for the very kind introduction. So let's hope that this works. Cool. Can you see my screen? Yeah, cool. Yep. Fantastic, great. So today I'm going to be talking about AI for self-driving, and I'm very excited to be here at CMU today. And I have a lot of material. So what I'm going to do is try to go and give you a high-level description of how we went around building different autonomy systems. More than going into the details of any one of these, different works that we did. Okay, so bear with me. There's going to be a lot of stuff, but hopefully, through a comprehensive sort of description, you actually see what we were thinking and what we did. So the first thing to think about is if you want to build self-driving cars at a scale, right? What is the sort of the things that you need? So on one side, you need to be able to build these vehicles, right? This is what you observe on the left. You need to build them at the scale. And these vehicles are not the same as just regular vehicles, right? They have to have things like redundant steering, redundant compute, etc. if something goes wrong. You also need to build the self-driving system. This is basically the brain of the vehicle, which is what probably most of you are excited about. But also, if you want to build this at the scale, you need to operate these vehicles, and you need to be able to deploy them such that you can bring people or things from point A to point B. So you need a network. At Uber, we definitely know how to build networks. We are developing the brain of the self-driving car, and we partner with other partners in order to do things like building vehicles at the scale. We don't actually build our own vehicles. Now, today, during this talk, I'm only going to be talking about the brain. And in particular, I want to mostly be talking about autonomy. So how to build a system that is able to react to everything that's happening in the scene and drive safely. And hopefully I will have enough time at the end to just show you some stuff on simulation, which I'm very, very excited about in order to test how well your autonomy system is doing. So without further ado, so let me tell you a little bit about what are the different approaches to build autonomy for self-driving. So a very popular approach in academia is to train a neural network for the types of driving, right? And the input to such a system is going to be a set of sensor measurements, where it's the LiDAR, images, and the output is the information necessary for the self-driving car to drive. This can be, for example, a steering command and acceleration. The advantage of such a system, right, is that it is very easy to get a prototype with just a few lines of code on your favorite, PyTorch or TensorFlow sort of framework. Furthermore, the good thing is that this system is trained for the end task, right? Your loss function is at the end of the network, which is the task of driving. However, this paradigm has several key disadvantages, which makes it very difficult to impossible to actually build a real system that you can deploy in the real world. First, it is very difficult to incorporate prior knowledge, and thus to make this system respect the rules of traffic. It is also it has also no interpretability, which poses a problem if the system were to if you want to validate the system, and also for safety, and in particular if the vehicle did something that actually resulted in something bad, right? It's very hard for you to explain why this is the case and how to improve the system afterwards. An alternative, which is what you typically see in almost all self-driving car companies, is to go for a traditional software stack. And this traditional software stack is basically composed of a set of modules that can executed one after another. And this works as follows. Every fraction of a second, the vehicle senses the environment, right? And this is illustrated here with a bird's eye view of the LiDAR point cloud, right? As if you were on the top, just looking down. And the first thing that these vehicles do is that you localize with precision of a few centimeters into where you are in the world. This is done not only in order to route the vehicle from point A to point B, but also in order to exploit high definition maps, which gives you a lot of prior knowledge about what you potentially are going to see in the environment before you actually look at your sensor measurements. Then the perception system is then responsible for estimating where the different actors are in the scene. So here I'm depicting with rectangles vehicles and circles for pedestrians. And then the prediction system basically takes the output of perception and estimates the potential trajectories that these actors might be doing in the next few seconds, typically the direction of the planning horizon. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. And then the control system then ensures that the trajectory we intended to follow is the one that is executed. And the reason that we need to do this is that there might be deviations due to unaccounted factors, such as friction or the fact that we might have very simplistic vehicle dynamics that are not realistic. Now, this whole process, going from localization, perception, prediction, planning, and control, typically is repeated every fraction of a second, something like 100 milliseconds. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations that we lack in this end-to-end approach that I explained before. And it's easy to incorporate prior knowledge, right? We have these intermediate representations where we have a lot of intuitions about what they should be modeling. However, reaction time is typically large as computation adds up, right? You have to execute these models one at a time. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack. So engineers are going to be manually adjusting their algorithms because somebody else changed something, that goes in some model before them. Furthermore, the different models are typically not trained for the end task, and thus improvements in model performance do not translate to better driving. For example, if you're a perception engineer, you typically look at your PR curves and then you want to detect everything great. But at some point, the fact that you improve these detections doesn't mean that you're going to drive better, because maybe you improve in vehicles or things that are actually not going to interact with the SDV. So what we are building on Uber ATG, so our vision is, which is different than what you see in the competitors, has the advantages of both end-to-end and traditional engineering approaches, but without inherently their respective drawbacks. So in particular, we believe in a single AI system that can automatically adjust itself to any changes. That's increasing significantly the developer productivity, since we don't need engineers to talk to engineers, saying, hey, I changed something in the software stack. As computation is now shared across modules, the resultant reaction time is going to be also much lower. Furthermore, we are going to keep these interpretable intermediate representations, and as a consequence, we're going to allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, since it's end-to-end trainable, every improvement that we do within these models is going to result in better driving. Our first attempt towards this vision focused on developing approaches that can do joint perception and prediction. this is basically 2/3 of the software stack within a single algorithm. So I'm gonna talk about a couple of generations of this, of what we did. We started what is now 3 years ago with a very simplistic approach, where the idea is we're gonna have a bird's eye view representation of the past and the present view data sweeps. And we are basically gonna have a convolutional network that is able to do detection as well as regress the trajectory of these detections across time and into the future. So this is within the planning horizon. And we're going to use 3D convolutions in this representation in order to estimate both detection as well as regression. This ended up actually working really well. And despite the use of 3D convolutions, you can actually run this still in real time, where the results that I'm showing here are run in 35 milliseconds. So one thing to notice from the video is that the task of driving is extremely difficult in the sense that there is so many things happening in the scene, right? There is many vehicles. There is oftentimes more than 100 actors acting in the scene at the same time. In this video, the same color means that we're actually also doing tracking, which can be done also in an easy manner end-to-end. And these waypoints that emanate for every bounding box is basically a prediction into in the next second what these different actors are going to be doing. Okay, so that you get a sense of how well we predict the future. Now, the longer that or the farther away that these points are, the faster the speed that we predict, right? And if we see a single point, it means that we predict that this particular actor is going to be static within the next few seconds. So that was our first attempt, and that was a big deal in the sense that you can already do 2/3 of the stack with a single algorithm. So that actually improved productivity a lot. The next generation that we built had two main changes. One was that for perception and for prediction, it's actually important that if you have access to high definition maps, you should exploit them in order to detect better and predict better. So in this case, we designed a two-stream architecture that process on one side the voxelized LiDAR point cloud, and on the other side the high definition map. And the other change that we're going to do is that we're going to do not only detection and prediction into the future, but we're going to enhance this network to also predict intentions. So I'm going to showcase this with a video, and I want you to focus on the bottom of the video, where the idea here is that the colors that you see associated with the bounding boxes represent a particular set of actions. So the more yellow it is, the higher the probability of simply driving. The more red it is, the higher the probability of being stopped. The more purple it is, the vehicles, the higher the probability of being parked. And it's important to know that although the actions are pretty similar of park and being stopped, it's important to make a distinction because it matters for planning in terms of what will be the maneuver that you will do, condition of which one of these two actions is. The arrows also represent the probability of doing things like changing lanes, keeping lane, or making turns. So this is great, right? Now you have a way to do joint perception and prediction, and you start to get the semantics about intentions that could be very useful for planning, right? But there is a fundamental problem with this kind of approach. And I'm going to illustrate this with a video. So what happens is that the way that we predict this is once you do detection and you have the feature representations for every actor, we predict them in an independent manner, right? We regress basically these trajectories. And as a consequence, what happens is that you can get collisions within your predictions. And we know that in general, collisions between actors is something that happens very rarely, right? So what we like to do is to build a representation that is able to exploit the fact that there is interactions between these different actors. And for example, in this scene, they're not going to collide, but one actor is going to yield to the other actor in order to avoid this collision. So the question is, how can we do this within this joint perception and prediction problem? So the idea is going to be that we're going to enhance the way that we do the predictions. So we're going to start in a similar manner by having a voxelized representation of LiDAR. We have our high definition maps. We're going to go through our favorite network. And basically what we're going to do now is based on the detections that we have, we're going to compute rotated regions of interest where we're going to pull features. And this is going to give us a representation for every actor. And then we're going to use a graph neural network in order to model the interactions between all these different actors. Okay, and then we're going to do this with a fully connected graph. And basically, we're going to do rounds of message passing such that every actor is going to adjust the predictions based on what every other actor is intended to do. And at the end of it, of this graph neural network, which is especially aware, because it's very, very important in driving where everybody is related to each other. At the end of the network, we're going to predict a probability distribution or a marginal distribution over each one of these actors. Okay, so that actually worked pretty nicely. In this case, we're going to model this probability distribution with a Gaussian. And here it's interesting that the graph neural network actually is doing something similar to Gaussian belief propagation, where our messages are sort of like Gaussian, are related to, I guess, the parameters of Gaussians. And what you see here is that we are able to predict in a way that results in less potential collisions as we have these longer term predictions now. And when I say collisions here, I mean collisions of the predictions for every actor, not the SDV per se. So now we are able to take into account these interactions, but there is still an underlying problem in this kind of model. And the main problem can be illustrated with the following example. So imagine you're in this situation where there is two vehicles. One is on the road and the other one is going to merge, right? And then you can think of there is multiple ways that this scene might unroll. In one example, the vehicle that is on the road on the top, right, is going to just continue, and the other vehicle is going to yield to it. Have the opposite situation, right, where the vehicle on the right is going to accelerate and it's going to get incorporate on that road before the other vehicle arrives. We can also have a situation where both are cautious, right, and basically they're both going to arrive at the same time. Or potentially, if we actually sample the marginal distribution, another explanation will be that both accelerate and basically arrive in a collision. So despite the fact that we have this notion of we perform interactions in order to decide what these actors might do, because of the inherent multimodality of the problem, our marginal distributions do not really, so although they are computed, take into account the interactions, we cannot use marginal distributions for the probability of the trajectory of every actor such that we have a consistent explanation of what's happening in the scene. So despite this reasoning, motion planning is stuck in the sense that cannot piece together all the scene in a way that is a consistent, socially compliant manner. So we need to do something more sophisticated. So the next version, what we're trying to do is to generate these socially consistent samples across the full scene, right? And the way to do this is actually to model the joint distribution across all actors, right? So this is great if you are able to do so, but there is a computational complexity, right, that grows exponentially a priori with the number of actors, right? So this is the reason why we weren't doing it in the first place. So the question is, can we design a model that can run inference in real time such that we can actually compute samples that are consistent across the full scene? And the idea is that you want to have samples as you see on the bottom, right? Where one explanation here is that if you look at the example on the left, right, it's the same scene, and these are just two samples of how the future might unroll. On the bottom, you see the cars or vehicles that are on the bottom are actually going to make a left turn. And as a consequence, all these vehicles on the right and on the left are not going to move or move very little. On the right-hand side, you see another explanation of the scene where basically the vehicles that are on the bottom are not going to move. And instead, the traffic that goes across the scene is going to be moving as, and crossing this intersection, right? So you see that these are socially compliant. These are very possible explanations of the scene, but you need to take into account how everybody behaves with respect to everybody in order to make these kind of predictions. So let's see how we can do this. So the way that we're going to achieve this is by introducing an implicit latent variable model. And the idea, as before, is that we have our high definition maps, we have our representation of the LiDAR point clouds, and basically you do detection, you extract features, right? And we can consider these features as this X representation here, which is a feature representation for every actor. And the idea is that we're going to have an encoder that takes these feature representations and it's going to create a latent representation of the scene. And this latent representation, we're going to actually do it in a distributed manner. And the reason that we do this is because we want to capture the case that there is a variable number of actors possibly interacting in the scene. And then we're going to have another graph neural network as decoder that basically is deterministic, and given a sample for the scene, can actually decode into the trajectories for every one of these actors that are actually socially compliant. Okay, so inference is very simple, right? You do a feed-forward network, you do your graph neural network, you sample from P of Z given the representation, which is the hidden representation for the graph neural network, and then basically you continue forward propagating through the graph neural network decoder to get your trajectory samples. This is something that you can also train end-to-end, okay? And I'm not gonna go into many details, but the idea is that you have a loss for detection, you have a loss for the prediction, and you also have this KL loss, which is basically saying, this is like a CVAE, if you wish, saying that you know, your prior should be as close as possible to the encoder. So now that you have this latent representation, right, what we can do is take two extreme samples, and then we can interpolate between them. And that's what you're seeing over here. So I'm basically taking two sets that are samples from the model, and then I'm looking at what will happen if I vary Z and I decode, right? So you see that although we have a single latent variable, right, is representing how this, you know, the possible explanations of the scene will vary in a socially consistent manner. Now, so this actually ends up not only having this more socially compliant behavior, but in practice, it works much better than anything out there for the state of the art. And it's particularly good, no surprise here, at having less collisions for the predictions than any of the models published before this work. And let me show you some qualitative results. This is what you can see here, right? So we have these nice multimodal distributions, right? Which are simply generated by sampling the latent variable and then multiple times, right? And pushing through the network. And you see that, you know, we have also a very nice understanding of the map, which is actually pretty hard in terms of these prediction models. So we can do these long-term predictions that you see over here that are pretty realistic. And as you see, like typically the predictions are very socially compliant, as I mentioned. You can go one step forward, right? And then look at, so this is great from a prediction perspective, but does this actually result in better driving? So what we're gonna do now is that we're gonna hook up this joint perception prediction to a motion planner, and then look at motion planning metrics. And we're gonna do the same for a whole variety of models in the literature, and then compare, in this case, the metrics in terms of things like safety, right? Whether the percentage of complex scenarios where our vehicle will end up in a collision. In this case, it's open loop, okay? So it's not real collision in the sense that you will replan every 100 milliseconds. And also results in much more comfortable or more comfortable driving than any of the previous approaches that we observed. While the progress being more or less the same, which is basically the progress means that you want to go somewhere, right? Whether you are over conservative or you are actually arriving at destination more or less at the same time as everybody else. Cool. So I mentioned, right, a whole variety of methods of how to start with something very simplistic for prediction, right? And how we can make this, you know, how can we modify the model to be more and more complex, such that we take into account all these interactions. The next thing I want to talk about is, you know, despite, you know, all the advances that we've seen in the literature in terms of perception and prediction, this is still an extremely difficult task. And the question is, can we actually have a different way to improve the performance of these systems, such as we are not bound but by what a single vehicle can actually do? And the answer obviously is yes. So let's see into what the problem is and what can we do about it. So on one side, the problem is the following, is that, well, where things are close by and they're not occluded, then we have a lot of evidence of what is in the scene. So we can actually do perception really well. Things that are far away or very, very occluded, what happens is that we see only 1 lidar point, 0 lidar points, maybe a couple of pixels, right? And it's extremely hard to actually detect those objects and predict accurately what they're going to be doing in the next few seconds, right? However, sorry, this is occlusion, I guess. However, if we were to have a fleet of vehicles in the same area, and these vehicles were able to communicate to each other, right? What will happen is that we will be able to see through occlusions. We will be able to see with much more evidence, what is for a single vehicle at range, right? And we should be able to improve these joint perception and prediction systems to be much better. So let's see how we can do that. So one of the first things that we need to think about is, well, if we want to do vehicle-to-vehicle communication, right, such that we can exploit what other vehicles see in order to get better perception and prediction. So the first question is sort of like, what is the kind of information that I should transmit such that I can actually improve as much as possible the accuracy of my perception and prediction, but at the same time, I need to take into account that the information that I should send shouldn't be too cumbersome, right? Because I'm going to have limited bandwidth typically when I do this communication, right? So I should be able to provide information that is very condensed, right? That is very compressed, but at the same time, it's very useful for this task. And the question is, how can we design such a compression algorithm and also the aggregation functions such that we can do vehicle-to-vehicle communication? So let's look at what are the possibilities. Probably the first thing that comes to mind to everybody is that, well, what I can do is I can just transmit the sensory information that every vehicle sees. And I'm illustrating this here with the lidar, right? Where every one of the vehicles in the scene is just sending all the lidar point clouds that it observes to any other vehicle that is a self-driving car in this scene. And on the right-hand side, I'm just aggregating the lidar point clouds so that you see how we can now see through occlusions, right, as well as see at range, right? So this is, this is great in terms of that all the information is preserved. However, the problem here is that it's not compact, right? I observe typically, hundreds of thousands of points at every 100 milliseconds. So it's gonna, there's gonna be a delay in the transmission in terms of, sending this information, right? Because it's just, too much bandwidth. The other problem is that, well, if you think of the receiving car, now it's going to receive all these lidar point clouds from everybody, or cameras, or images, all of the sensors, and then suddenly needs to process all this information, right? So it's going to be very hard to actually do this in real time. And the more that more vehicles are there in the scene, the worse this gets. So this is not a good solution. An alternative is, well, instead of just sending the input, I can send the output of the system. Right, so I could try to do this joint perception prediction, right, and then just send where I believe the different actors are and my predictions into the future. Now, the good thing about this is that it's very compact, right? It's very cheap to transmit, so that's great. But it's very limited in terms of the expressiveness of the information that they are actually conveying. Also, if you think about it, right, there's a lot of information that is lost if you only send bounding boxes and maybe some notion of uncertainty of those bounding boxes, right? So this is also not the best possible representation. So instead, what we look at is, can we actually transmit intermediate representations of this joint PNP system such that these representations are compact, so we can learn such that they are compact, right? They preserve all the information, and at the same time, this system, if you think about it, allows for distributed computation. So let me explain this by illustrating how the method works. So imagine we have 3 vehicles in the scene, right? There is the vehicle on the top that basically, let's assume that is the central vehicle that we're going to look at, and there is 2 other vehicles that are within the range that we're going to receive signal from them. Now, what we're going to do is that every vehicle is sensing the environment. So it has its own LiDAR point cloud, right, as you see, observe here. And every vehicle is going to start doing computation of the sensor information it receives. Given these intermediate representations, every vehicle is going to send that, is going to compress that, sorry, and it's going to send that to the medium, right? It's going to broadcast that. And then what we're going to do is that we are going to receive messages from other vehicles. We're going to decompress them, and we're going to create a spatially aware graph neural network. And this graph neural network is going to be different for every one of these vehicles because my neighbors are different than your neighbors. And in this graph neural network, what we're going to do is aggregate the information that is transmitted by every one of these vehicles in a way that is spatially aware as well. Because since we have these bird's eye view representations of the intermediate representations, basically it represents still this spatial location or information. And this spatially aware GNN is also going to be, it's going to understand transmission delay so that we can handle the case that this is an asynchronous process where not everybody sees the scene at the same time. And then basically we're going to use this in order to generate good representations, exploiting the information about what other vehicles see. And then we're going to further do detection, joint detection and prediction using this information. So that's basically how this works. And we can do this. So the way that we actually train and showcase this is going to be in simulation. And later in the talk at the end, I'm going to show you our simulator. But what you observe here is different scenes where we assume that only a small percentage of the vehicles is they are self-driving vehicles. Right, and the idea is that you want to perceive everybody else in the scene. With different colors here, you see also the different LiDAR observations that the different vehicles will see in the scene. And the fact that some of them disappear, it means that they are not anymore sort of on the broadcast range for the ego vehicle that we are looking at. So it turns out that, first of all, no fusion means that if we don't do vehicle-to-vehicle communication here, it turns out that you can have extremely significant gains in performance by doing vehicle-to-vehicle communication. So any of the different strategies that I talked about before results in huge performance boost. And here the AP for the no fusion is particularly low because we look at all possible actors, including those that are occluded for that vehicle. Okay, so it's an extremely difficult prediction problem, but it's still the one that you need to solve in practice. And as you can see here, in terms of detection, which is the first metric, as well as L2 error, doing this with this vehicle-to-vehicle communication with V2VNet, which is this graph neural network stuff, ends up being where you have the best performance, while at the same time you have sort of the best compression ratio. Now we can look at how this changes as a function of how many self-driving vehicles you have in a single scene. And what is remarkable is that the error, as well as the performance for the detection, as well as prediction, scales linearly with the number of vehicles, right? So, and the other thing that is interesting is that this sort of, in the case that you don't observe any single vehicle, this sort of defaults to the case of where basically you're just exploiting your sensors, right? So there's a huge gain here, as the world gets more and more self-driving vehicles to really exploit the fact that you can communicate. Now, what is good about this strategy I mentioned with V2VNet is the fact that not only you get, in general better performance, but it's actually very robust to, in this case, imperfect localization. So here we are looking at on the bottom is detection, on the top is prediction, as how the performance of detection and the prediction error will change if you were to have positional errors in terms of the localization system of the different self-driving vehicles, right? If I were to be, say, 0.3 meters away, 0.4 meters away from what I think I am, right? Will I be robust to this? And you see that this graph neural network is actually a much better way to associate, it's a much better way to deal with this imperfect data than the standard sort of LiDAR fusion or output fusion. Importantly, is that doing this is also very robust to things like delay messages. So this is the fact, so what we're seeing here is like if you think about it, every vehicle goes with the cycle of its own lidar, right? However, there is no coordination between the lidars of the different vehicles, right? So every vehicle is gonna observe and it's gonna send. So there's gonna be also a delay in terms of when that is gonna be received on the other end, right? So the thing to note here is that on the left is detection, on the right is, in this case, is prediction. You see that V2VNet, again, the use of this graph neural network stuff allows, and the intermediate representations allows you to be much more robust to time delay than these other approaches that have a hard time into understanding observations over different time frames. Cool. So I show you a whole bunch of ways to do joint perception and prediction. And I'm gonna change gears to try to add now the next item, right, which is motion planning, right? I was telling you before this vision of I wanna do joint perception, prediction, as well as motion planning, right, in a way that I get these interpretable representations and I'm able to train this end to end. So let's look at what are the different models or techniques that we build in order to try to do this. So our first approach was actually fairly simplistic, which is to say that we're gonna treat the joint perception, prediction, and motion planning problem as a multitask prediction problem, where every one of these goals is a task, okay? So we're gonna have basically a neural network, right? Again, it's gonna take these versatile view representations and the HD maps. It's gonna predict some feature representation, right? As you see, hopefully you see my mouse here in the middle. And then I'm gonna have different headers doing detection, predicting different timestamps into the future. And then I'm gonna have another header that is gonna create a cost volume for planning. Okay, so this is a little bit similar to what we were doing in the more simplistic joint perception prediction, right at the top. But now we're gonna have an additional header which is this cost volume. So let me explain you what this cost volume is with some illustration. So this cost volume is gonna be, it's three-dimensional and it has width versus height on one side, and then it has time here on the other dimension. And what it represents is basically the cost that I will incur if my self-driving car was to be at any possible location and at any possible time in my planning horizon, okay? So the idea is that if you have a trajectory, what you need to do is just index in this cost volume for the different waypoints, right, the cost, and then basically you can sum the cost and that will give you what is the cost of this particular trajectory, right? So you can think of this is like a structured prediction problem, right? Where you're basically in a non-parametric way, you're modeling the potentials as a function of all the variables of this trajectory, okay? And this is something that you can do very efficiently in the GPU, right? Because this is nothing but indexing in the volume and then doing average pooling, right, a summing, right? And you can also do inference in a very simple way by saying, I'm gonna have a whole bunch of trajectories, right? I compute my feed-forward network, I can estimate by detections, I can compute my, my planning horizon, right? And then for every potential sample of what the self-driving car should do, I'm gonna basically estimate its cost. I'm gonna compute all those costs, and I'm gonna just do, I'm gonna take the argmin as the trajectory with the minimum cost. And that will be my solution for my planning, for my planner, okay? So very, very simplistic way to do this. It turns out that this is also easy to train end to end. You can have a loss for detection and prediction, and you can have also a loss for planning. Now for planning, you need to be a bit careful because you cannot supervise directly this volume, right? Since you don't know you don't have a perfect planner, right? You don't have a planner to start with. So you don't know which locations are good versus not. So what we do is just use max margin as our loss, where basically you can think of this as imitation learning, right? Where you wanna be as close as possible to what the human did. And then you're gonna pay a cost, which is the test loss, proportional to things like, did I collide? Do I respect the rules of traffic, etc. And this is the way that end-to-end you can train the whole network to do detection, prediction, as well as planning. So let me show you with a video what this does. So this is a complex representation, so bear with me. So we have the data point class, the map, we have the detections, the predictions into the future, and this colorful thing is basically a projection of this three-dimensional volume into 2 dimensions. And I'm only showcasing the areas of low cost for the SDV, which is in red, okay? So what you observe is that this cost volume is very multimodal, right? In this case, we can change lanes, right? Or we can continue straight, right? And you see how it's reacting to the actors, right? In this case, we could turn or we can continue straight. So that's one of the advantages, is that, you know, it can learn all these different behaviors without, you know, explicitly incorporating them. It actually learns to do very complex maneuvers like nudges, as you see over here, which is one of the most difficult things to do with self-driving, is nudging around obstacles. And it does this only by looking at trying to imitate what humans did, and having some bounding boxes labeled over time, as is the, you know, typically the case on perception systems. So this was our first attempt, and, you know, it's great in the sense that it allows us to actually easily do joint perception, prediction, and motion planning, but it has you know, a set of fundamental problems in the design. The first problem was that this perception and prediction was done in a way that was deterministic, meaning that we predicted a single trajectory for every actor. It was also problematic in the sense that the planner does not explicitly, is not explicitly conditioned on the prediction. Right, given the features computed by the network, they are independent, right? This is why it's treated as a multitask problem. So, you know, it was easy to do, but actually it's not great in terms of, it could be inconsistencies between what the planner did and what the perception and prediction said. And more importantly, so we have this non-parametric cost volume that was fully learned, and the prior knowledge from the humans was only in the loss function. So there's no guarantee that this planner that I just presented before is going to do the right thing, it's going to drive safely. So what we're going to do now is try to address these issues by doing something a little bit more sophisticated. So we want to use the prior knowledge, we want to explicitly condition on the prediction, and we're going to use multimodal, socially consistent representations. So how can we do that? We can do, as you see the design on the top here, we're going to do a more sophisticated sort of like modular approach, right? Where the feature representations are gonna again influence detection, prediction, and planning. So that's great. But at the same time, the output of detections are gonna be used for prediction, which are gonna be used for planning. Okay, so that now we have the system that actually is fully explainable, and at the same time is consistent. And what's interesting in this work is that the way that we're gonna do prediction is going to be through a deep structure model. So it's a generalization of Markov random fields where the potentials are coming out of the neural network. And this Markov random field is going to represent with every node, every one of the detections, right, every actor. And the representation is in terms of the possible trajectories that these actors can take. So this is in general continuous, but we approximate it with you know, a set of samples from every actor. In this case, we use 300 samples for everyone. And basically, then it's a discrete MRF. And then you can think of the prediction model, the inference in the prediction model as simply doing message passing, which is something you can unroll as a neural network in order to compute the marginal distributions for every one of these actors in the scene. And then this is passed to motion planning, where basically is looking at minimizing the expected cost is the expectation over all these possible trajectories of the actors. So that worked much better. And what is interesting is that as you predict into the future for the different actors, now you have these nice multimodal distributions. So you're gonna be much more aware of possibilities, and they'll be much more safe as you take decisions for the planner. The other thing that is interesting is that you see when things are very easy, like you're continuing, sort of it's very clear that you're gonna continue straight, you have these much more unimodal distributions for your predictions, While when people are going to take a turn, right, there is many ways that they can do so. So you have these more multimodal distributions. And so this end up working much better than the neural motion planner. We have much less collisions in terms of the prediction, but more importantly, we have a much better motion planner because in the previous case, right, in the neural motion planner, what happens is that if you predict the broad mode, basically you have the potential of colliding with an object, right? You predict that somebody is going to be going straight instead of changing to your lane, right? That could be very, very bad. And in general, we have almost no collision rate with respect to predictions. So this is more socially consistent. Now, so this is sort of one step forward. Right now, we can do these socially compliant things, but we still have an issue. And the issue is very simple to actually see, which is that these models are based on detection, right? Like once I detect, I do prediction, right, and I do planning. And so imagine you're in a situation like this, you're the red car, right? And there is this car making a turn in front of you, right, taking a left. So if you were to, for whatever reason, not detect this vehicle, you might want to actually speed up, right, and then go in the intersection, and this might lead to a collision, right? And what happens is that there is actually chances that you don't detect an object, right? For example, if it's below the threshold, or you simply suppress it with your non-maxima suppression, right? So there is a fundamental issue of safety when you do this detection-based approaches to autonomy. And most of the software stacks are actually based on this detection-based approach. So we can do something different, which is, can we actually get rid of detection while still having interpretable intermediate representations? And the idea is very simple, is that we're going to follow sort of the same architecture of our voxelized radar, our high definition maps, but instead of trying to do detection, what we're going to do is that we're going to directly predict semantic occupancy layers. And what this semantic occupancy represent is the probability that any particular location in a space will be occupied at different times in the planning horizon. Okay. And you can do this by, in particular, we do this by recursively sort of reasoning about the semantic occupancy, right? So given the observations up to this point in time, we can predict in a recursive manner what will be this occupancy for the next t time steps, right? So we take the first time step, second time step, all the way to the planning horizon t. And then we can design a motion planner that has a combination of, that is able to use the semantic occupancies and is also able to use more of the safety-based cost functions. So in this case, the planner will be very similar in the sense that we were going to set sample a set of trajectories. We're going to evaluate these trajectories and pick the one with the minimal cost, where the cost now is looking at, we're going to try to avoid occupied regions in the future, right? That is predicted with our semantic occupancy. We are going to try to drive comfortably. We're going to try to follow the route to arrive where we wanted to go. And we're going to do things like try to not deviate from the lane center, not go off the road and stuff like that. Okay, and then we will select again, we will sample many trajectories, right? Thousands, tens of thousands, and we will select the one with the minimum cost. And again, this is something that you can train end to end. In the planning side with max margin loss, and in terms of the semantic occupancy, you can use cross-entropy loss for this raster representation of occupancy. So this actually end up working really nicely in both open loop and closed loop. I think here I only have open loop results for you. But again, you have much less collisions. You are more similar to what the humans did. And then you have more comfort or similar comfort in terms of jerk, lateral acceleration and progress. So let me show you this with a video. And this is open loop, okay? You observe up to the first frame, and then I'm gonna just show you what we have predict for the future and how the future unroll, okay? And you see here that this what is interesting about these occupancies is that you don't have any more this representation of detections and associated uncertainties, right? Instead, you have this much more flexible representation of uncertainty. And in this case, we have many, many semantic layers, capturing very interesting things like, for example, if vehicles are in the coming lane or they're in conflict or on the route of the SDV, etc., such that the planner can actually have a lot of flexibility into how to use that and plan accordingly. Cool. So I've talked mostly, I've talked about autonomy a lot, right? So hopefully you saw a little bit into how we went and designed all these different models from joint perception prediction using vehicle-to-vehicle communication to neural motion planner. And in the next 5 minutes, I'm going to talk about simulation, and then I will conclude there. So what is important when you develop these autonomous systems is how do you actually know that you're doing the right thing? There is like 3 types of tests, a way to test the autonomous system in the industry. The first one is structural testing, which is typically done in the test track, where it's high fidelity, is with real, I guess with the real SDV, and then some fake actors like the mannequin here. You can create some sort of at-risk situations, but not super safety critical, right? Because you're testing a real system. And it's not scalable in the sense that actually it's very expensive to do any of these repeatable tests. An alternative is what is called replay or log simulation, which is what we typically do as perception people, right? Which is we have training data or we have data that we have observed, and we try to look at whether we predict what we observe, right? So did we do the same as a human? For example, how we will test the autonomous system. Now, it's high fidelity in the sense that the sensors represent the real world. It's not reactive in the sense that the only thing you can test is what you have observed, right? If your plan deviates from what you did in the first place, you can't test how safe that plan is, because you cannot regenerate what the sensors would have seen if you were to execute that. Safety critical, you cannot really do safety critical things in the sense that this is from real logs, so you don't want to test things where you have an accident, for example, right? In the sense that you don't want to generate accidents in order to say, how you will react to the situation where potentially you could have an accident. And this is, sort of not scalable in the sense that you need to observe the world, and for getting to the long interest is difficult. The alternative is to use simulation, right? Which the problem is that, so it's reactive, you can test safety critical because it's in the virtual world, right? So there's no problem there. But the problem with simulation is that it's extremely hard, or these days, you don't really have simulators that have high fidelity. So I'm going to talk a little bit into what we have done in order to build this high fidelity simulation such that we can really test the end-to-end system. So what happened in industry, right, is you have the sensor data, you have the autonomy stack, and then typically when it goes to simulation, people start with bounding boxes and trajectories, right? And then you test either your prediction system or your marginal planning system, but you never test the full system. And you typically test it with the scenarios that are ground truth, meaning that you're going to be overconfident. Ground truth meaning that you have the right predictions, right? So you're going to be overconfident into how well your system reacts to your perception system, right? Because your perception system is not going to be perfect. So this is problematic, right? So we would like to have a closed loop simulator that is able to simulate how the sensors will see the scene. And the problem here is that traditional or typical approaches don't have the right level of fidelity. Okay, so let me explain first the data, and then I will show you a couple of videos with cameras. So what do people do is in the industry, they take artists, they build these virtual worlds or virtual cities, and then they use typically physics, right? For example, raycasting in order to say, to render, how the vehicle will have seen this scene. So the problem of this is that to create these worlds is time consuming, it's very expensive, it doesn't scale, you have limited diversity, and it's not realistic when you render. So it's a big difference between for the perception system. So our philosophy is very different. And it's been based on a very simple concept, which is we have driven millions of miles, or, so we have already observed the world. So what we can do is we can use this data that we have observed in order to generate how the world looks like. And this is, as you see on the top, how the static scenes look like, as well as how the dynamic objects look like. And we can do this in an automatic manner. And we will create, we can generate automatic how the specific intersections and rows that we are intended to work to drive in look like. So this is a particular intersection in piecework, I believe. Maybe maybe you guys can see where it is. I'm not so familiar with piecework, I guess. And then we can do the same for vehicles, pedestrians, bicyclists, motorcycles, right? We have these tens of thousands of these assets that we automatically generate. And they are really very diverse. Like, as you can see here, we observe so many different interesting vehicles, right? That now we can create simulations we have this library of static areas, right? Where we have drive, which is, full cities. We have these 3D assets for dynamic objects, and we can generate scenarios by putting these assets with particular traffic situations, right? And then we can use a combination of physics and machine learning in order to render how our self-driving car will actually see the scene, okay? And it turns out that actually this works really well. On the left-hand side, you see our simulator. On the right-hand side, you see a real scene. And on green, you see the output of the perception system. So although it has never seen simulation before, our perception system behaves the same on simulation and in the real world, right? So the domain gap is almost none. And therefore, we can actually test the autonomous system. Now, you can ask the question, how does this compare to other simulators like Carla? So if we look at the performance of the system for real data, and if you train on Carla, there is a huge performance difference of 25, in this case, 25 points, absolute points of IOU. So it's not realistic. But our simulator is there is only a 1% difference. You can also exploit this to increase, to train on simulation or train on a mix of real data and simulation. So on the middle is if I only use real data. On the right is if I use a combination of real data for the same amount and simulation. So you see that you can further boost the performance with this data augmentation by using the simulation. What is more important is that we can create these safety critical systems, the safety critical scenarios. In this case, we are creating a scenario that never happened of this car that is coming out of occlusion, that in this case, we have this big truck or bus that is occluding our view, right? And then we can test how well our full system will actually handle this type of scenarios. And we can do this at a scale by testing the same type of scenario in all different locations and different variations of the appearances of these things, as well as the velocity profiles, etc. You can do the same thing for cameras. Okay, and I'm just going to show you, as I said, just a couple of images, and I will conclude. And so one of these, in this case, what we're going to do for cameras is we're going to insert what we call actor injection. We're going to insert fake things in the scene, and these fake things are going to be 3D aware. Like one of these vehicles is fake. Do you know which one? So that one was fake. There is one more here. So we do this in a 3D aware manner such that we can actually mimic exactly the occlusions as you see here. In this case, this actor is fake as well. And we can do this, since it's 3D aware, we can do this consistent over time, where we can actually just generate these scenarios within the logs that we have captured. Okay. So in this case, we reconstruct all these assets from logs, and then we put them to perform different maneuvers in other logs. And since, as I said, everything is 3D aware, you can actually simulate how different cameras will see the same scene as well. And all this is actually consistent between what the LiDAR sees in the simulation and what the camera sees. Okay, so just to conclude, right, so today I talked a lot about autonomy, a little bit about simulation, but there is a lot of more things that, areas of focus that we do in the lab, and there is so much more to do. I think there's been a lot of advances recently in self-driving, but, to solve the self-driving at this scale, there is, need for a lot more research. Thank you.
Thank you very much. That was That was great. So I guess we have time for a few questions. People who want to ask questions can feel free to click the raise hand button under participants or type your question into the chat. While we're waiting for people to do that, I can ask first question. I'm curious your thoughts about prediction-based approaches that involve sampling different possible futures. And the concern I have with that category of approaches is that we have to be safe even with, for self-driving cars, even with regard to fairly low probability events. Like if something has a 1% chance of happening or 0.1 or pretty low, even probably much lower than that even, which means that we would have to generate a lot of samples to find these such events that we need to be safe with regard to them. So what are your thoughts on how we can handle that?
Yeah, so if you just, I guess model based on, I want to explain the likelihood of the data, and then you get sample from that model, then you will have the problem that you are referring to. Now, if in your sampler, you do something different, for example, you make the sample to be encouraging diversity, then you can actually get the low probability events even with a small number of samples. And that's one way that you can handle the problem you're talking about, yes.
Got it, cool.
Now, the other thing, so you don't need to necessarily use samples with these techniques. If you, in the occupancy case, you're directly modeling the probability of occupancy. So for the planner, you're already having the rasterized version. So you even, you avoid that problem altogether.
Right, but then you don't get the interaction effects of like either A or B happens.
That's right.
Yeah. Cool. Okay, I think Chris Catani has a question.
Yeah, thanks Raquel. That was an awesome talk. Always feel like you've already finished everything after I hear you talk. But so I'm kind of.
You mean that I always talk too much? That's what you mean?
No. I mean, it's amazing, right? The breadth of the research. I'm thinking a little bit ahead when we talk about the full end-to-end pipeline. When you have planning and control, like all mixed into one. And what I'm thinking is that at some point, like the system is going to have to interact with the world. Like it's going to have to do a little bit of exploration, a little bit of learning, just like we do when we're driving, kind of make small mistakes and fine tune over time. And so there was, I think on your table, when you were talking about the simulated data, there was the reactive part. And I think we need, at some point, we'll have to step out of simulation and actually like see what other people do. And so I was wondering if you had any thoughts on like how we're going to do that. Like, how do we do that in a safe way? Because I think we need to do that to be able to really, really improve, the full pipeline.
Yeah, so I guess the question is, how much do you need to observe in the real world in order to learn how to react to it versus can you actually do this in simulation in the way that, you have less and less reliance on the real world. Now, in order to do this in simulation, one of the difficulties is that you need high fidelity not only on the sensors, you need high fidelity on the behaviors, right? You need to be able to have also the diversity of those behaviors, etc. Now, typically, the way that in industry people also look at this is by doing, a lot of, decomposing the problem into, say, scenario families, right? And then looking at for those scenario families all possible variations and see whether, and then assume that the world is a composition of these things. And then hopefully, if you're good on those things, then you will be good on the composition. That's a way to decompose the problem as well. So I think there is a lot that we can do in that direction. And the things that I haven't talked about today, we do a lot these days in the lab is adversarial stuff, physically realistic adversarial, even in behaviors, and to understand what you don't do well. Because making mistakes in the real world is definitely the thing that you want to avoid, at all costs if you can. Yeah. But it's this interplay, right? But I think that simulation is so important such that you don't need that. because that's when it gets more dangerous.
Yeah, that makes sense. Thank you.
Cool. So just a reminder, everyone, I put a link in the chat about the post-seminar reception and gather town. So people who, so I encourage everyone to go there. Let's see, yeah, so anyone who has a question, again, feel free to click the raise hand button or type your question into the chat. And in the meantime, I can ask another question. Just a very general question. You framed, at the very beginning of your talk, you said you can either do this end-to-end approach, it's fully differentiable, which is great, or this modular approach, but then you propose this alternative where you have modules that are learning-based methods, but you can also maybe backprop through the whole thing. So I guess my question is, what are your thoughts on non-differentiable algorithms? There are many such algorithms that exist in the world. Do you think that there's always a differentiable version of such an algorithm that is almost as good, or we don't really need non-differential algorithms? Or what's your thoughts?
No, I think that if if you were able, if as a community we were able to have better reinforcement learning algorithms, then that will not be a problem, right? And in the in our work we also look at it's not just about the algorithms, also the loss functions might not be differentiable. Right. And then we have used reinforcement learning in other case. Now the problem is that those RL is very sample inefficient and it doesn't work as well. Right. So but it's definitely is a very interesting direction that will expand the set of possibilities for your intermediate sort of models here. Right here, I mean, there are things that a priori don't look differentiable, but many things you can actually approximate and differentiate. Mm. Right, so that's also, and the question is how much do you approximate there versus how much do you lose if you don't train end-to-end? And what we observe is that if you look at the problem, right, there is a lot of stuff going on, say from the perception perspective, right, but most of the actors do not matter. And for some actors, it really matters in a very non-symmetric way. And if you don't look at planning, it's impossible for you to know that. And that's what you care about, right? And that's the, what the signal that is so good that you really want to propagate that, right?
Yeah, no, that makes a lot of sense. Let's see, I'll pause to see if anyone else has question. Chris, you've unmuted your mic. Do you want to ask a question?
I was preparing to clap.
Oh, okay. Got it. I'll ask one more question. You talked about V2V net and communication between self-driving vehicles. Do you think it's feasible to have communication between also just non-self-driving vehicles?
Yeah.
Big network with everything.
Yeah, one of my favorite topics, V2X, where X can be other vehicles, can be the environment. It's feasible, you can do stuff. I just wish that it was easy to collect that data. But definitely, there is a lot that you can do if, with information from other vehicles. And it can be all sorts of things, right? From traffic, accidents, construction, to more in-depth perception stuff and whatever. Extremely exciting direction. And I personally like also there is more and more things that are gonna fly. So that view from the top is fantastic for bird's-eye view representations. So yeah, there's plenty to do on that direction. Yeah.
Yeah, nice. It's a very inspiring view of the future, I think. Tarang posted a question in the chat. Do you see it, or do you want me to read it?
I see it now, I think. Just give me 1 second. Let's see. So it's about, I guess, failure cases, right? and identifying failure cases. So the kind of things that we are, let's see. So is if you have in your data, you have good metadata. It's very useful in terms of identifying, roughly what your system is not good at. For example, our planner cannot do well, as an example. Imagine it was unprotected left turns or whatever, right? So that's one good way to get more information, more semantics about what potentially could be done. We, as I mentioned before, we are looking a lot into adversarial examples in order to really poke the system until we find the failures. That's another very, very interesting direction, right? But typically these adversarials are not going to be, LP bound adversarial perturbations. That's not what happens in the real world, right? So how to also do it in a way that is, that you semantically you understand, I think is very, is also very interesting. So that's typically, with the metrics, with the simulation, and with metadata and the adversary stuff is how we identify problems. And then obviously, when you run these things on, say, on the test track, etc. as well. But yes, I said you want to do things as much as possible in simulation. And then we can do other things like causal analysis of what caused what was a failure versus not. That's another very interesting direction of research. Hopefully that, Tarang, that answered your question.
Yeah, I think the question.
Yes, so my question was that you initially said that we generally modularize all of the components because it is more interpretable. So if we have like a single component for perception, prediction, and planning, then does interpretability go for a toss?
Yeah, so if you let's see, so single component for perception and prediction, so I don't think any interpretability goes, in the sense that what is perception is prediction on time zero, right? So by definition, there is no difference between the tasks there, right? So that the interpretability didn't go away. Now, if you notice between perception and, between perception, prediction, and planning, we actually maintain the modularity in these approaches, right? And they were our planners are they're called PLT planners, which is a very well-known traditional plan. So the advantage of doing what we're doing is that the costs can be very complicated, right? And then you can mix this safety handmade costs or safety-aware handmade cost with this learnable cost. And you can bound them such that safety is guaranteed and things like this. And then suddenly you can do much more complicated stuff while maintaining all the advantages of traditional stuff. So imagine if you don't train end-to-end, right? How are you going to use these complex representations? How are you going to fix, those feature functions that are high dimensional? That's not going to work well, right? So that's what this gives you. So you haven't lost anything. And the other thing that is very interesting is that you can think also of these neural motion planners as a way to train perception and prediction systems. You can chop the network at that point and not use the planner and use your production planner. And that perception and prediction system will be better than if it's just trained for perception and prediction anyways, right? So again, you haven't lost anything. The composability is there, but you get this end-to-end training that allows you to also train much faster instead of manually adjusting things.
Thank you.
And that's the difference with the first sort of approach, the academic of or reinforcement learning of pixels in and then controls out. There is nothing you can do. In the ones I show, right, you can really, it's very modular, so you can decide which model to use.
Adam, do you want to start?
Yes. I have a quick question about the forecasting. So you mentioned that you like your forecasters to be socially aware, so that all the actors are looking at what the other actors are doing. And this helps you avoid collisions, but collisions of the predictions. But are you also able to predict when an accident is about to happen?
So we haven't looked with these models at that in particular, but you definitely can do so by looking at your, you know, the I guess the overlap between the distributions, right, of the different actors. So you could do things like that. You can use also like reachability and other things to look at that as well. Yeah, interesting question. We haven't looked at that, but definitely you can use this. Yeah, we are now looking at this in the context of how to understand when the vehicle is doing the right thing by looking at how other people should react to you. Right, so if everybody has to react all the time to you, then you're probably doing the wrong thing. Right. Imagine, you know, if everybody has to slam on the brake for not having a collision, right? So your vehicle is doing something wrong. So we are looking at these kind of things, and also reactive planners. And reactive planners are planners where, so your prediction system here is not conditional planning in the examples I show you. Right, but if you take a decision of what the plan maneuver, right, that's gonna change how the others are gonna react to you. Right, and that allows you to do things like being much better as when you have tight, to squeeze tight in spaces, right, you can actually do this much better. If you wanna drive in, say, some Southeast Asia city where there's a lot of traffic, etc., this is actually fundamental. But you need to be careful into, you shouldn't be too aggressive or too confident on the other vehicles reacting to you, while at the same time, you know, taking into account the reaction. Yeah, there is a lot of like, still so many open problems, as I mentioned before, of, you know, going forward on this. Yeah. Yeah, great question, Adam. And good to see you.
So yes, I don't see any other hand raised at the moment. So maybe we'll stop here and people can continue to chat in the Gather town. So yeah, so let's all thank Raquel.
Thank you.